Hello, I wanted to give you a couple more examples of homomorphisms of rings. So here we go. The first example that we looked at in class was the example of a function from the complex numbers to itself via conjugation. So we're taking the complex conjugate of a number. A plus bi gets sent to a minus bi. So let me remind you what an automorphism is. Well, it's got to be a function from C to itself. It has to be a homomorphism, meaning that it's got to preserve addition and multiplication. And it has to be onto and one-to-one. So it's a bijection. Now this preserves addition and multiplication. You've seen examples of stuff like this before in linear algebra. We thought about linear transformations. They say that L of the sum of vectors is the sum of L of those vectors, and a scalar multiple of a vector gets sent to the scalar multiple of L of that vector. So we've played with this kind of idea before, although it may have been a while ago. Onto and one-to-one, one of the examples we'll look at will show that something is onto but not one-to-one. So we'll do a little bit of a review of that too. Okay, so here's another example of something. This is a function, but it's not going to be a homomorphism. So I'm taking the q with the square root of 3, sending it to q with the square root of 5 by taking a plus b square root of 3 to a plus b square root of 5. So I'm really just swapping out square root of 3 and square root of 5. We would call this a function that fixes q. Rational numbers, like a, get sent to themselves, and it's really only the thing that's got the square root of 3 attached to it that gets sent somewhere else. Now, I claim this doesn't preserve multiplication, which means I'm going to show an example of two things that I multiply. I apply f, and I get some value, and that value will be different than what happens if I apply f to my two elements first and then multiply them. So here we go. Let's take a look. I chose to look at f of 1 plus the square root of 3 times 1 minus the square root of 3 because I'm lazy and differences of squares are easy to work with. So if I multiply 1 plus the square root of 3 and 1 minus the square root of 3, I get 1 minus 3. So I'm really applying f to the element negative 2. So f of negative 2 is negative 2 because it doesn't have any square root of 3 part attached to it. However, if I take f of 1 plus the square root of 3 and then f of 1 minus the square root of 3, and I multiply those, I get 1 plus the square root of 5 times 1 minus the square root of 5. Now that's 1 minus 5, which is negative 4. Negative 2 is not negative 4. That's pretty good. We rely on that to make sure that counting actually works. And this tells us that this function f, although it's a fine function, it doesn't preserve multiplication. So the algebra gets messed up if we apply f. And since we're in an algebra class, that's kind of a bummer. All right, here's one more example. Let's take this function g. G starts with an integer and takes it to its equivalence class modulo 5. Now, I claim that this is a homomorphism of rings, and here's why. G is a function. Whatever, every element gets sent to its equivalence class. Every element goes to a specific equivalence class, so it's well defined. If I consider what happens when I look at the operations addition and multiplication, I've got to remember how we define those. But when we apply g to x plus y, we get the equivalence class of x plus y. And as it happens, that's the same thing as the equivalence class of x plus the equivalence class of y, which is g of x plus g of y. So addition is preserved. And similarly, if I look at this product, well, the way we said to multiply equivalence classes was to take the product of their representatives. And this tells us that multiplication is also preserved. So we've got ourselves a nice little ring homomorphism here. If I give you some target equivalence class, like A mod 5, and say, tell me something that maps there, we could just say, all right, take the representative A, plug it into G, you get A mod 5. And that means that G is onto, given any target in Z mod 5. And really, I know there are only 5 possible targets. The equivalence class of 0, the equivalence class of 1, the equivalence class of 2, of 3, of 4. Then I can map there by plugging in 0, 1, 2, 3, or 4. Or if I plug in 15, I'm going to go to 0. And if I plug in 16, I'm going to go to 1. That's fine. Now, it's not one-to-one because there are lots of different ways that I can get to the same equivalence class. So g of a and g of 5 plus a both go to the equivalence class a mod 5, but a is not the same integer as 5 plus a. They're not equal. One's 5 more than the other. So although g is onto, it's not one-to-one. And that means that these rings, z and z mod 5, are not isomorphic. Now, in some way, that kind of has a truthy feel to it, right? One is infinite and one only has 5 elements. So how could they be isomorphic? How could they have the same structure? Well, this is the algebra that justifies that sort of truthy feeling that we're having. All right, more videos coming up with one more proposition that helps us out on our quest to look at the solvability or insolvability of the quintic.